Hi, welcome to Ushendra's engineering tutorials. It's another important numerical which is a continuation to designing a basic meters. Basic meter as a voltmeter, and a concept which cannot be neglected. It's the question is over here, please make a note. It's about calculating the errors in voltmeter reading, right? Prior to that, we need to have some initial stuff to support our discussion, right? So this is the circuit. RA equal to 25 kilo ohm, RB equal to 5 kilo ohm, and the supply voltage being 30 volts. Making use of the potential divider rule, it's a now the question is measure voltage across RB and what would be the error while making use of meter 1 and what would be the error while making use of meter 2. That's the question. And before going that, a little basic fundamental. What would be the drop across RB making use of the traditional method potential divider rule? It's how to evaluate that. VRB will be equal to VRB drop across resistance RB. How it is equal to this resistance, the drop, the resistance across which we are trying to measure the drop. It's a 5 kilo ohm upon the total resistance. The total resistance being 30 kilo ohm into the supply. It's a 30 volts. Okay, so it's a 30 volts. Now what happens here? Kilo gets cancelled, kilo ohm gets cancelled, and 30 also. We are left with 5 volts. It's a 5 volts. Now the drop across VRB will be 5 volts from the potential divider rule in the absence of making use of voltmeter 1 and voltmeter 2. Now what will be the reading while we make use of voltmeter 1? Come here, the specification of the first meter is given as the sensitivity is here. S is equal to 1 kilo ohm per volt, and the range, the meter range here, if it's a voltmeter, it's a 0 volt over here, it's a 5, and it's a 10 volt. The scale would be like this, 10 volts, the maximum voltage it can handle, the maximum voltage it can read, 10 volts, and the range is given as 0 to 10 volts, right? So to proceed ahead with the numerical, we need to evaluate the internal resistance of the basic meter of meter 1 and meter 2 individually. Then we have to proceed. What happens with the error, what amount of error is produced by individual meters, right? So in order to evaluate the internal resistance of the basic meter, we need to make use of the equation for sensitivity. S is given as sensitivity. What is that? Sensitivity S is given as 1 upon IFSD, the full scale deflection current, and in the given question we are not given with IFSD, so we have to make use of this equation. What is that? 1 upon, it's a current, and V by Rm. So now this goes up, Rm by V, and from here this very expression we can evaluate the internal resistance of the basic meter. That's given as Rm is equal to here, Rm will be equal to, sorry it's not, Rm will be equal to, it's dividing, going that it multiplies S into V. What is this V? Now Rm, from this very expression, Rm will be, sensitivity is given as 1 kilo ohm per volt, 1 kilo ohm per volt multiplied with the voltage. What value comes into the picture over here? This one, the maximum value. The maximum value comes into the picture. It's a 10 volt, right? 10 volts. Now gets cancelled, and Rm, internal resistance of the basic meter, Rm will be 1 into 10, and what units are left over? Kilo ohms are left over. This is the internal resistance of the basic the voltmeter 1, right? So what we interpret from here, Rm equal to 10 kilo ohm, what it does in how is it related to this numerical? Let's see over here. So when you are asked to connect the voltmeter, how do we connect across RB? Across, I gave you the answer, across, right? This is how I'm drawing it in dotted lines intentionally. This is how we connect the voltmeter, right? This is how we connect the voltmeter across RB. Now during this action, now this connecting the voltmeter like this one, that means that we are introducing the internal resistance of the basic meter here. We are introducing the internal resistance of the basic meter like this. It's here. Now this one, it will be more clear. We are introducing the Rm, how it's looking like, we are introducing the internal resistance of the basic meter in parallel with this one, RB. We are shunting the RB with the internal resistance of the basic meter. Now what happens is, how much it is? 10 kilo ohms, being 10 kilo ohm. Now the resistance across QR will be changed to some other level, right? The equivalent circuit would be looking like this one. Here 30 volts supply as it is, no change over that, and even the 25 kilo ohms as it is, nothing to do with this. Now here have a halt and look at that one. Look at the circuit modification. How the equivalent, the resistance between QR would change to new level, that's given as 5 kilo ohm in parallel with 10 kilo ohm. So how to write this one? It's a 5 into 10 by 5 plus 10 kilo ohms. Okay, 5 plus 10, that would result, it's a kilos ohm. Even this is in kilo, this is in kilo. So the final result would be, you just do the calculation, it should be 3.33 kilo ohms. Now this says that we need to interpret that the resistance between Q and R changed to a new value, it's a 3.33 kilo ohms. Now this is a modified circuit after the first voltmeter is introduced across R and B. Now we evaluate for the drop across RB. Now this will be our new RB. So VRB, now after introducing the voltmeter 1, VRB would be 3.33 kilo ohm by total resistance, it's 28.3333 kilo ohm into the supply voltage as it is 30 volts. Okay, so here kilos and gets away everything. Simplifying this one, the new VRB is how much? It should be 3.5 and we are left with volts. This is the indication given by the voltmeter 1. In the absence of this one, it's exactly 5 volts, okay, making use of the traditional method. After introducing the voltmeter, this is the amount of voltage which is indicated by the voltmeter. Now how to evaluate the error for the voltmeter? It's evaluating the error. It's what expression do we have for error? Calculating error, it's a true value, it's a 5 volts true value minus the indicated value 3.5 volts upon the true value 5 volts. So simplifying this one, it's a 0.3 volts and converting that, it's a 30%. Guys, we have a 30% error while measuring the drop across RB, making use of the resistance 1, I mean voltmeter 1. Please make a note. Now considering the second voltmeter, the specification of the second voltmeter is given as S is how much? Sensitivity is, it's a 20 kilo ohm per volt, and the range again between 0 to 10 volts range. Okay, once again we need to evaluate the internal resistance of the second meter also, then we have to proceed with the problem. So Rm would be the previous expression, Rm would be S into V, which is equal to 20 kilo ohm per volt into 10 volt. It's this one, so we have it's a 200 kilo ohm. Volt got cancelled, 20 into 10, it's 200 kilo ohm. Now when the voltmeter is connected, when the second voltmeter is connected across RB, that indirectly introduces a resistance of 200 kilo ohm in shunt with the 5 kilo ohm. What would be the equivalent now? It's equivalent will be 5 kilo ohm parallel to 200 kilo ohm in this case. So the resultant would be 5 kilo ohm into 200 kilo ohm upon 200 kilo ohm plus 5 kilo ohm, and the resultant would be, you do it, it should be 4.88 kilo ohm if I'm not wrong. Right now the equivalent circuit will be looking like this. Here it's no change in the 30 volts supply, no change in 30 volt supply, it's as it is. Even the 25 kilo ohm resistance, no change, but here the equivalent resistance would be dropping to how much? 4.88 kilo ohm. Now what would be the reading across RB? Now new RB is this much, so what would be the new VRB? VRB will be equal to how much? 4.88 into the supply, 4.88 kilo ohm. I'm very sorry, I'm taking back, gali mat dena, I forgot that. 4.88 into 4.88 kilo ohm into 30 volts upon the total resistance of the circuit. Now it's a 25 kilo ohm plus 4.88 kilo ohm. Now this is the value for new drop across RB with the new value of equivalent resistance of this one. So simplifying this one, it should be VRB should be equal to how much? 4.88 into 30. It should be nearly 4.9 volts something. Kilos gets cancelled here. This kilo gets cancelled. We'll be left with voltage. Now it's a voltage VRB. Now this will be the new 4.9 volts. It's the measured. So what will be the error? How to evaluate the error? It's a measured error. Once again, error is given as measured true value, right? True value minus measured by true value. What's the true value? It's 5 volts minus measured, how much it is? 4.9 volts by true value 5 volts. Again, volts gets cancelled. Guys, previously in the error I might have done a mistake. I might have told it's voltage. No, it's voltage gets cancelled. It's a constant value. Error will be now simplifying this one, it should be 0.02 and it's nothing but error E being 2%, right? Previously it was 30% for the first meter. Now for the second meter it's 2%. More precisely, it's the percentage error being 2%. So what interpretation to be done with all these results? The first voltmeter having the sensitivity with 1 kilo ohm per volt gives rise to 30% of error, and the second voltmeter having a sensitivity of 20 kilo ohm per volt gives rise to 2% error. So what interpretation to be made in order to avoid the loading effect? Now all the discussion comes under the category loading effect. In order to avoid loading effect, in order to reduce the error in the measured value, we have to select a voltmeter having a sensitivity of a higher value, higher range, higher value of sensitivity is to be preferred. So hope you understand the numerical. Support me with your valuable share and subscription. Thank you for being with me. Thank you. Stay home, stay safe.